Welcome back to control system lectures. This lecture is for the time response of first order system. Now, once we studied the different test signals for doing the analysis or performing the analysis of a control system in the time domain, now we will see what is the time response of a typical first order system. This is a first order system. The first order system here is g of s is a forward path transfer function and h of s is a feedback transfer function. G of s is equal to 1 divided by st, it is a first order system. And now the closed loop system, that is r of s is the input and input is the forward path transfer function. G of s is 1 divided by st and this signal is feedback, that is h of s is 1, it is a unity feedback system. The closed loop transfer function is written as, we know, g of s 1 plus g of s h of s. So, replacing g of s as 1 divided by st and this is 1 plus 1 divided by st into 1. Since h of s is 1, it is a unity feedback system, we can see that the signal is fed back for reference and this is 1 divided by st plus 1. So, the closed loop transfer function here 1 divided by st plus 1 is a closed loop transfer function of a first order system, whereas the forward path transfer function is 1 divided by st and the feedback value is 1. So, with unity feedback, the first order system is written as 1 divided by st plus 1. Now, what is the response of, now we shall see what is the response of first order system. In the previous lecture, we have seen that there are certain test signals which are applied to a control system to know the response of a system. The first one is the step input. So, Cs upon Rs, that is the closed loop transfer function of a typical first order system, is derived as 1 upon st plus 1. So, C of s is the output and R of s is the input. So, now the R of s input is a unit step input. So, we are going to check the response of the first order system with a unit step input. C of s is equal to, this is the closed loop transfer function and C of s is equal to replacing the shifting R of s to the other side of the equal sign. Now, since input is a unit step function, R of s, the Laplace transform of a unit step function is 1 by s. Therefore, the input is a step input and the output of the system, that is C of s, this output of the system C of s for a unit step input is 1 divided by s st plus 1. So, this is in the s domain. Now, we need to know what would be the value of the output of a first order system to a unit step input in terms of time domain. So, we are going to find the value of C of t, that is the output of the function C of t for a unit step input. So, applying partial fraction expansion, we get that 1 by s minus t divided by st plus 1. So, this second term can be rewritten for convenience as 1 divided by s plus 1 by t. Now, taking the inverse Laplace transform, we get that the inverse Laplace transform of 1 by s is 1 and the inverse Laplace transform of 1 divided by s plus 1 by t is 1 minus e raised to minus t by t. So, the response of a first order system for a unit step input is 1 minus e raised to minus t by t. So, this is the typical first order system, and response of first order system, it has an exponential term e raised to minus t by t. Now, let us examine what happens. So, in place of, we have seen that the response of a first order system to unit step input is minus t by t. Now, when this value t is equal to the time constant capital T, when t is equal to the time constant capital T, then we get the output C of t is equal to 1 minus e raised to minus 1, and this is 63.2% of the final or the steady state value. So, when the time is equal to the time constant t, the response of the first order system is 63.2% of its final value. So, we just replaced the time t with the value of capital T, that is the time constant. Now, here we can see that this time constant indicates how fast the system reaches the final value. Final value here means the steady state value, as we know that a system has two responses, that is the transient response and the steady state response. So, we are talking about the steady state value. Now, smaller the time constant, faster is the system response. Now, as this time constant corresponds, as there is if the time constant is large, then it means that the system is sluggish, that is it does reaches its final value, the system will reach its final value, but if the time constant is large, then it is termed as a slow moving system or a sluggish system. Now, since the output response or the output is having an exponential term, now as the output increases exponentially from 0 to final value, the slope of the curve, that is the slope of the curve, now is we will see how the curve can be plotted. So, this is the typical graph. Now, as we have seen that when t is equal to capital T, the output C of t is equal to 63.2% of the final value. Now, this when shown in the graph. Now, what does this mean? Now, this is the time axis and this is the output. The y axis is the response, that is C of t of a first order system subjected to a unit step input. So, this represents, this graph is C of t, which is 1 minus e raised to minus t by t. It is having an exponential term here. And what is the slope of the curve? The slope of the curve here is, how do we obtain the slope of the curve? We differentiate the output value, and at t is equal to 0, we get the slope as 1 by t. So, that is what is indicated here. The slope of the curve is 1 by t. Now, this t, the duration from 0 to t is known as the transient response of the system, and this is known as the steady state response of the system. So, the first order system subjected to a step input will have a typical characteristics of this kind. This is the 63.2%, that is 0.632. Now, we will see how do we have obtained these values. Now, as can be seen here from the exponential curve, it is clear that the magnitude of the output response is 63.2% of final value in one time constant. Now, if you again use the same equation of the time response, that is C of t is 1 minus e raised to minus t by t, and replace t with 2t, that is time constant, 2 time constants. Then what about the magnitude? We are replacing C of t or finding out the response of the system, time response of the system for e raised to minus t by t. We are replacing the small t by 2 time constant. So, what we get? 86.4%. Similarly, 4 time constant, replacing t by 4t, the magnitude of the output reaches approximately 98% of its final value for 4 time constant. So, replacing this t by 4t, we get time constant multiplied by 4, and it can be seen that the value of the response, that is C of t, that is the time response of a first order system subjected to a step function, is 0.981. So, this graph indicates 4t. This means that the magnitude of the output voltage reaches 98%, approximately 98% at 4 time constants. So, when the actual output reaches 2% of the desired output, it is said that the steady state has reached, that is the time constant is equal to, the time is equal to 4 time constant. So, this is a typical graphical response of a first order system. The time 4t is known as the settling time for a first order system. T is equal to 4t is known as the settling time. So, this much of value is obtained at 4 time constant. Therefore, 4 time constant is known as the settling time. Now, what is the error? What will be the error of the first order system, and how is error calculated? Error is calculated with the value E of t is equal to the reference input which you have given as the step input minus the output. So, here this 1, this value, this is the reference input, that is the unit step input, which is having a value 1, and this R of t is 1, whereas what is C of t? C of t is 1 minus e raised to minus t by t. So, what is the error? Error is e raised to minus t by t. The term E of t, that is the error value, this steady state error is obtained by simply applying the limit t tends to infinity. We need to know what will be the steady state error as time approaches infinity. So, for a first order system, we can see that the steady state error as time approaches infinity is equal to 0. ESS, normally it is represented by ESS, the steady state error when time approaches infinity is equal to 0. Similarly, we will now see what will be the response of a first order system when subjected to unit ramp input. Now, unit ramp input, as we have seen, the unit ramp input R of t is represented with a time value t, and the Laplace transform of a ramp signal, ramp input function, is 1 divided by s square. So, here as mentioned, the output of a closed loop system, as we had seen, how is the response of a unity feedback first order system. This is the R of S and this is 1 divided by St plus 1. This is the output C of S. So, C of S is equal to 1 divided by St plus 1 into R of S, and the input is a ramp function since we are checking the response of a first order system when subjected to unit ramp input. Therefore, the C of S is now equal to 1 divided by S square, simply replacing R of S with 1 divided by S square. Now, after applying the partial fraction expansion, C of S is equal to this value 1 by S square minus T by S plus T into 1 divided by S plus 1 by T. We have rearranged the function with after applying the partial fraction expansion. Now, taking the inverse Laplace transform, we obtain the time domain value, the output, that is C of t of a first order system when subjected to a ramp input is equal to t minus the time constant plus time constant e raised to minus t by t. So, what is the error here? Error of a first order system when subjected to a ramp input. Now, we can see here that this R of t is a ramp signal, R of t is a ramp signal and this is the response of the system C of t, and this is the input R of t, which is t. So, this represents the input and this graph represents the output of the system. Now, we can see that what is error? Error is equal to E of t is equal to t, that is the reference or the input given is the ramp function, which is equal to t minus the value of the output. Therefore, t is equal to E of t is equal to t 1 minus e raised to minus t by t. So, this is the error value. Now, what is the steady state error? Steady state error is limit t tends to infinity, e raised to t is equal to t plus t e raised to minus infinity in place of t. So, the steady state error ESS is equal to t as obtained by applying limit t tends to infinity. So, it can be seen that there is a error between the input and the output, and that value is t even at infinity, even at t equal to infinity. The steady state error is equal to t, where t is the time constant of the system. For smaller time constant, this is a point which is to be understood. For smaller time constant, steady state error will be small and speed response will increase. Now, similarly, if we are using a parabolic function, the only difference here is we are now mathematically checking out, we are now mathematically listing out what will be the output response of a system when subjected to different test signals, that is the step function, the ramp function. Similarly, now if you are applying a parabolic input, that is the parabolic function here is, sorry, this is a parabolic function. Parabolic function here is R of s is equal to, this is the Laplace transform of a parabolic function, which is equal to 1 divided by s cube. So, what is the response of the system? In the similar way, we are applying partial fraction expansion and taking the inverse. The value here will come out to be C of t is equal to t square by 2 minus time constant into t plus t square minus t square e raised to minus t upon the time constant. So, this is the typical output of a first order system subjected to parabolic input. Similarly, if you are using the fourth signal, that is the impulse input, the impulse input is the Laplace transform of the impulse input is R of s is equal to 1, and applying R of s is equal to 1 here, the output of the system in terms of the s domain function is 1 divided by s t plus 1. So, just rearranging the term, this becomes t is taken out, s is equal to 1 divided by s plus 1 by t. Applying the inverse Laplace transform, we obtain the time response function, that is c of t when subjected to an impulse function is equal to 1 by t e raised to minus t by t. So, in this lecture we have seen that what will be the time response of a first order system. The forward part transfer function of a first order system is 1 divided by s into t, and applying different inputs we have checked what will be the response of the system when response of a first order system when subjected to the different 4 types of standard test signals. Thank you.